The word work may have variety of meaning in ordinary language, but physics give a very specific meaning to define what is done when force acts on an object and the object moves through a distance. Work done on an object is just equal to the product of the constant force done on an object and the displacement as the object moves or changes its position. The force and displacement are parallel in this case. For example, a person is moving a cart loaded with boxes of raw materials from the warehouse to another office. This is an example of work in everyday language, and also an example of work in physics. Suppose that this person pushes the cart a distance of 50 meters by exerting a horizontal force of 30 newtons. The work done by this person is 50 meters multiplied to 30 newtons. This is equal to 1500 newton meter. This unit is equal to joules. Thus, the work done is 1500 joules. There are instances when force is exerted between an angle theta of the direction of force and displacement. Consider this situation. A person is pulling a crate along the floor. Force is exerted in this direction, with an angle theta. For it to be parallel to the displacement, we need to find the component along the x-axis of this force. Using the trigonometric equations, the component of the force parallel to the displacement is equal to F cosine theta. Therefore, work is equal to the product of displacement and F cosine theta. Always remember that these equations describing work are derived from constant force exerted to an object. Energy has a very broad definition in science. In this video, we will define energy as the ability to do work. This is not very precise and not valid for all types of energy. But it is valid for mechanical energy, and that's what we are going to talk about. The mechanical energy gives a very fundamental connection between work and energy. One type of this energy is the kinetic energy, defined as the energy of motion. To derive the quantitative equation for kinetic energy, consider this example. A car with mass m is moving in a straight road with an initial speed v1. It accelerates uniformly to a speed v2 by the constant force exerted on it parallel to its motion over a displacement d. Work is equal to force multiplied to displacement, while force is equal to mass times acceleration. Therefore, work is equal to mass times acceleration times displacement. We need to define the acceleration in terms of velocity. We can use this kinematics equation for one-dimensional motion. By substituting this to the work equation, the translational kinetic energy is now equal to 1/2 mv squared. If it is possible for an object to have energy by virtue of its motion, or the kinetic energy, it is also possible for an object to have an energy associated with force that depend on the position or configuration relative to its surrounding, or the potential energy. The most common example of this type of energy is gravitational potential energy. To have idea about this energy, here's an example. It is the hungry Syrian wanderer's birthday. He received packages from his supporters. He found that some boxes are heavy. He tried to lift one box vertically with mass m. In order for him to do that, he needed to exert an upward force at least equivalent to the box's weight, denoted as mg. To lift the box without acceleration to a vertical height h, from y1 to y2, he must to do work, represented by this equation. Work is equal to the external force that is mass times acceleration due to gravity, times the vertical displacement or height h times cosine 0 degrees. Cosine 0 degrees only tells that the direction of force is upward. You don't have to worry about it, it's just equal to 1. There is gravity acting on the box as it moves along the vertical height, and is work on it equal to gravitational force times the vertical height times cosine 180 degrees. Cosine 180 degrees tells the direction of the gravitational force is downward, and this is equal to -1. Since energy basically means the ability to do work, we proved that there's work acting on the whole system in the example given. And from that we can say that there is gravitational potential energy. This is defined as the product of weight, mg, and its height above some reference level. Why I use the term system is because potential energy does not only belongs to the object alone, but to the entire system. This means that the system consists of the box, as well as the earth that gives reference to the vertical height as the box is lifted and the box's weight. In the previous video, we talked about gravitational potential energy, and derived the mathematical equation involved. As a continuation to the topic potential energy, there are other types of potential energy, and is also associated with force. Remember, Newton's third law of motion states that there is an equal and opposite force reacting to a force being exerted. Applying this to the concept of work and energy, the change in potential energy is generally associated with a particular force equal to the negative of work done by that force if the object is moved from one point to a second point. Then again, the change in potential energy is the work required of an external force to move the object without acceleration between 2 points. All these definitions can be used analogously to another form of potential energy, that associated with elastic materials. For example, the spring has elastic potential energy because it can do work on a ball when released. The string can be compressed or stretched to a distance x. There is force exerted by the hand on the spring, denoted as Fp, and is equal to kx, where k is the stiffness constant. At the same time the spring also exerts force on the hand, denoted as Fs, and is equal to -kx. To calculate the elastic potential energy, this time work is defined as the average force times distance being compressed or stretched. The average force is equal to the initial position, which is equal to 0, plus the stretched position kx, all over 2. Now work is equal to 1/2 kx times x. This gives 1/2 kx squared. Hence, the potential energy is 1/2 kx squared. There are several types of forces define different work in different ways. But there are two classifications of forces that express how these forces are applied. The conservative force means that when work is done, it does not depend on the path taken, but only on the initial and final position. Potential energy can be defined only for a conservative force. Gravitational potential energy is defined as the work done to an object with mass m carried to a certain height h. In this case work is not dependent on the path taken, because it will take the same work even if the object will be carried in different path but with the same height. On the other hand, the non-conservative force is when work is dependent on the path taken. One good example for this is friction. When a crate is moved across a floor, from one point to another, more work is done if the crate is pushed along the semicircular path than the straight path. There is more work done in the semicircular path because the distance is greater. Thus work is path dependent because it has different magnitude whenever it is done in different way from the initial and final position. We can formulate a simple relation involving energy, as long as only conservative forces are acting on the system, and no non-conservative force are present. When there is no non-conservative force, work is equal to 0. From the work-energy principle, work is equal to the change in kinetic energy or the change in potential energy. This gives, the change in kinetic energy plus the change in potential energy is equal to 0. And since change is equal to final minus initial, we can further derive this equation to Ke2 plus Pe2 equal to Ke1 plus Pe1. This equation is the profound principle regarding the conservation of mechanical energy. Generally, the principle states that, if only conservative forces are acting, the total mechanical energy of a system neither increases nor decreases on any process. It stays constant, which means it is conserved. To apply this principle, let's solve a problem. If the original height of the rock is 3 meters, calculate the rock's speed when it has fallen to 1 meter above the ground. We cannot solve the speed by simply using the kinematics equation. We need a simple understanding of dynamics, involving work-energy principle. Using the equation of the conservation of mechanical force, we can manipulate the equation and define each terms into its individual definition. Ke is equal to 1/2 mv squared, while Pe is equal to mgy. We can cancel out the mass m since it does not change throughout the process. The initial height is 3 meters, while the final height is 1 meter. The initial speed is equal to 0. We are asked to calculate the final speed. The equation now looks like this. We have to substitute the given to calculate the speed at 1 meter. It is equal to 6.3 meter per second. Thank you so much for watching. I hope you learned something from this video. Click follow so you won't miss our new upload. There are other forms of energy that can be defined by kinetic energy and potential energy at the atomic or molecular level. Thermal energy is the kinetic energy of rapidly moving molecules. When an object is heated, the molecules move faster, caused by the increase in temperature. Chemical energy stored in fuel is the potential energy by virtue of relative positions of the atoms in a molecule. The bonds between the hydrogen and carbon atom of a hydrocarbon molecule store the energy. The energy stored in food must be released to be used to do work, usually through a chemical reaction. Other forms of energies are electric, magnetic and nuclear energy are also considered examples of kinetic and potential energy. Energy can be transformed from one form to another, and this involves transfer of energy from one object to another. The potential energy of a bent bow can be transformed into kinetic energy of the arrow. The potential energy of the water at the top of a dam is transformed into kinetic energy as the water falls. The kinetic energy of water at the base of the dam can then be transferred to turbine blades and further transformed into electric energy. And because energy is transformed or transferred from one form to another, then no energy is created or lost in the process. This leads to the law of conservation of energy. It states that the total energy is neither increased nor decreased in any process. Energy is transferred from one object to another, but the total amount remains constant. Power. This word has different meaning in other topics such as politics, military, sports, and education. In physics, power is the rate at which work is done. In a mathematical equation, the average power is simply equal to work done divided by the time to do it. Additionally, since work and energy are related, power can also be defined as the rate at which energy is transformed. The unit of energy is joules, while the unit of time is seconds. From the equation, power is measured in joules per second. This unit is equivalent to watt. This unit is used for electric devices. Power in watts is the rate at which the electric bulb changes electric energy into light energy. Watt is used for other types of energy transformations as well. In the British system of units, power is expressed in foot-pound per second. For practical purposes, larger unit is used, the horsepower. It is equal to 550 foot-pound per second, which is also equivalent to 746 watts. Energy and power have distinctions from each other. A person may be able to walk a long distance, but his energy is limited when he used so much of it. In this case, energy is measured On the other hand, the person may be exhausted after walking a long distance because he is limited by how fast the energy is transformed. That is, chemical energy from the food into mechanical energy. Thus he is limited by power. In this video, we will solve physics problem for the topic power. Problem solving in physics requires serious understanding on the principles, laws and theories. Power fall under dynamics in physics, therefore all principles involved in dynamics are applicable and useful to accomplish problem solving perfectly. It is important to understand the definition, as well as why and how the equations of each principles are derived. This helps to recognize and recall formulas easily. Here's the sample problem. A 60 kg jogger runs up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. Estimate the jogger's power output in watts and horsepower. To answer this problem, the first thing to do is to list the given in the problem. The mass of the jogger is 60 kilograms. The time it took to complete is 4 seconds. The height of the stairs is 4.5 meters. Now, let's list what is asked. We need to calculate power in units of watts and horsepower. Remember that power is the rate at which work is done. This is denoted by this equation: power is equal to work divided by time. The work done by the jogger is against the gravity. Thus, work is equal to mgy. Now that the equation is derived, we can finally input the given. Power is equal to 60 kilograms times 9.8 meter per second square times 4.5 meters, divided by 4 seconds. The unit kilogram meter squared per second squared is equivalent to joules. Hence, power is in joules per second or watts. The calculated power is equal to 660 watt. To convert this into horsepower, we need a conversion factor. 1 horsepower is equal to 746 watts. By means of simple dimensional analysis, power is equal to 0.885 horsepower. A car engine do work to overcome the force of friction and air resistance, in order to accelerate. Automobile engines are rated in horsepower because it is limited by the rate it can do work. In this video, we will calculate how much power is needed when a car climbs a hill. In this situation, power is in terms of force applied to an object with speed v. Since power is equal to work divided by time, while work is equal to force times displacement, therefore power is equal to forces times displacement divided by time. This is simply equivalent to force times velocity. Let's apply this equation. Calculate the power required of a 1400 kilogram car when it climbs a 10-degree hill, at a steady speed of 80 km per hour. Assume the retarding force of the car is 700 newtons. This is due to air resistance and friction that retards the motion. Therefore, the force required for the car to accelerate the car is equal to 700 newtons plus the component of gravity parallel to the hill. The component force is equal to mg sine 10 degrees. The calculated force is equal to 3,100 newtons. While the given speed is 80 km per hour or 22 meter per second. This is parallel to the force. Now, we can calculate the power. From the given equation before, power is equal to force times speed. Hence, power is 3,100 newtons times 22 meter per second. This is equal to 6.80 times 10 to 4 watts or 91 horsepower.